guys, can you hear me just fine? How about the back? You guys can hear me?
Perfect.
Okay, I don't know if you know this about me, but I was born with a little surround sound system in my vocal cords, so hopefully you have no problem in audio. How about online? Can you guys hear me? I'm gonna take that as a yes. All right, it really is my pleasure and privilege to be here today with you. None of you have to be here. This is not a forced class, so we're very excited to be with bright young minds like you who want to really grow and develop the quantum world and help fuel that fire in the furnace of innovation. And today, you're going to embark on a journey, on an adventure into your first superconducting qubit. And we're going to make it out of circuits like the ones that you hold in your phone, but using quantum electrodynamics rather than the more traditional Maxwell type of dynamics. Now, before we dive in, many of you here have helped contribute and make this workshop happen. It doesn't just happen by itself. I want to really give a huge thank you to the organizers. Speakers who poured blood, sweat, and tears into making this happen. I have never seen a workshop like this focused just on the design of superconducting quantum devices, and I find it exciting. I hope you do too. So let's get to know each other. Who here has heard of a quantum computer? All right, if you don't raise your hand, and I think I see you, I know that you lie about other things too. Thank you. How about, have you ever used a quantum device online, in your lab? Most of you, wonderful. How about, have you ever analyzed, designed, or made one? A couple of hands, okay, great. Because this is not the beginner track, this is the super cool beginner's track. So, excellent. Now, in this lecture, this really is an introductory and skill reaffirming lecture. I'm going to go over a lot of what Eli covered, just a lot slower and in a lot more depth and step by step. So in fact, my aim here really is to go step by step, focus on just one simple example and walk through it from the top of the world all the way to the nitty-gritty final detail. So we're going to not need to know much going in. Even if you don't remember what an inductor is or a capacitor is, that's okay. We're going to go over all of that. We're going to start super broad, and we're going to go very far and narrow in. We're not going to cover exhaustively. We'll chart a nice, narrow, deep path. This lecture is yours. So my intention is not to cover my 146 slides. It's rather to uncover at least a little bit. So if we make it to slide 20, I think it's a success. So please do interrupt me. And there's going to be excellent work later on with our two wonderful workshop folks and more, who I think are in the other room at the moment. So you'll put all of this into practice. Now let's step back and take a very big picture view before we dive into any of the concrete details. So what is a qubit? Well, a qubit has, in one picture, two energy levels, two discrete states. 0 and 1 conventionally. You also think of it in this other picture of a sphere, the Bloch sphere, which can represent the states that the qubit can take. The actual information is encoded in the direction of this arrow. And a qubit is also a physical device that lives in the quantum cloud. The qubit is all three of these. But what actually happens in this cloud? How do we make it? How do we run it? How do we design it? So let me take an example and start with these dilution refrigerators that you have seen many, many times. And unveil the golden chandelier. Of course, this is beautifully golden and shiny. It's just polished with gold. But in fact, everything you see here is just an input-output wiring. The only thing that actually matters is down here at the very, very bottom. And it operates at negative 273.13 Celsius, or typically 15 to 50 millikelvin above absolute zero. Colder than outer space. Now, at the bottom here, you have a can that in fact contains the only quantum object in this entire fridge. And that is a quantum chip or a quantum device. This is a picture from now many years ago from an IBM chip with 8 qubits. And in fact, if you look closer, you notice that there are repeating patterns and structures. There are little boxes here. There's 2 little rectangles. We'll zoom in a second. Each of these little boxes is a qubit. And in fact, you'll notice all these shiny squiggly lines. These are typically some metal traces on top of some silicon or sapphire or some kind of chip. And those are readout resonators to read out the qubits. So what you'll find is that there is a common pattern or common structure where you have a qubit coupled to a readout. Thank you, Eli. Hopefully you can see that much better now. And this may be a little bit more. So I'll let someone work on the lights while at least you can perfectly see this now, I hope. So this is the building block that Eli was talking about in his presentation. You see that all the same features repeat again and again and again. And then we're going to repeat them for 100 qubits, 1,000 qubits, 100,000 qubits and beyond, and improve them each time. So let's look at that Lego. Actually, let's keep it off because this is a second. It would be wonderful if we can turn the front lights off and keep it back. So here you see a different architecture. I don't want to expose you to just one particular type. Here's a Google style XMON. Oh, this is good. So for the moment, actually, we can keep it intimate and we can turn it back on. Here's an example Google architecture with 5 transmon qubits. Yet again, you see that there are these little, now the box is turned into a different shape, but honestly, the shape has very little importance, as we'll see. And then again, you have these squigglies, which just represent readout resonators, classical harmonic resonators. We'll talk about what that means in a second. And in fact, if you zoom in to one little piece here, this tiny, tiny little object right there, you see a SEM image. This is actually what it looks like at the 5 micrometer scale, but we have to zoom in even further to really see the Josephson tunnel junction that Eli introduced in his lecture. In fact, the only thing in this entire chip that actually allows us to access the true quantum nature of these chips is this little object right here. It's the overlap between this metallic pad sitting on top of silicon and that metallic superconducting piece. That's because you'll find out why in a few slides. Any questions?
Are those metallic paths perpendicular to each other?
Why are they perpendicular?
No, are they perpendicular?
In this case, they are. You see that, so there's a piece of metal right here, which sits on at the very bottom, and then there's another piece of metal, which is a little thicker in this case, and kind of comes over it, and you see the little bump. The exact.
They touch each other, or is there a material between them?
Yes, so they overlap, but there is a little tiny, about a nanometer or so, thin barrier between them that is an oxidized barrier. Good. So this is important because, in fact, this is the Josephson junction, which would be the key to almost everything that we will cover. But you don't need to know too much about the details of it either, because as Eli said, we can actually abstract away almost everything. In fact, if we look at these pictures, you can write down a circuit that you would have seen maybe in your middle school class or high school class on physics that looks a lot like capacitors and inductors coupled to each other. There's a little funny X symbol that represents that object that you just saw, the Josephson tunnel junction. It's an X because it's a junction. And you can begin to write down electrical circuit language that looks very much like your traditional physics pictures. But we're going to go from a world of classical circuits to the world of quantum circuits. And in fact, that's our adventure today. In all of our circuits, as Eli mentioned, there are a lot of building blocks. So you'll see these symbols again and again. And the goal will be to ultimately get to the block sphere and the qubit, which actually is supported by this physical device object here at the bottom. And then as Eli showed us, we also write down Hamiltonians. That is just another language, another picture to yet again tell us what this object is, what this object is, and what this object is. So you see all these objects in fact, trace and connect, and they represent the same physics at the end of the day. However, at different levels of abstraction, at the physical device level, the circuit level, the Hamiltonian level, and then the Hilbert space picture level. So zooming out, keeping our big picture view, what does it look like when you use your quantum machine today? Well, at the very top, you start with your laptop, which then submits a job to some cloud provider or your lab fridge, if you have one handy. That the signals go into the fridge and down the wires. They go all the way down to the bottom of the chip where you see the actual pieces of metal, which themselves actually support a notion of electromagnetic fields captured or contained and manipulated in electrical circuits, which themselves support the idea of a quantum Hilbert space and a qubit block sphere and C0 gates and control operations. We then manipulate the quantum state, which then through really understanding of readout of circuits, we feed a signal back through the chip, up the wires, through the lab computer, all the way back to your laptop. That's really the modern infrastructure for quantum computers in the cloud. And we're going to cover all of that in great detail in the next 2 hours. So I hope you're ready. So if you didn't get something, don't worry. We have 2 hours to go over. So what's on the road ahead? Well, we covered this picture of the cloud. Next, we really want to start at the very beginning. How do you really get a qubit from an atom or an oscillator in the first place? How do we actually create the transmon qubit? Of course, Jens Koch is in the room, so he should be the one to tell us. But I'll leave that to tomorrow's lecture for more depth on it. But how do we create these transmon qubits from the ground up? We're going to go in a lot of depth for it because all the devices I showed you were transmon qubits. They're not the only kind of qubit, but they're the most common you tend to find in the superconducting world. And all of that relies on classical circuits and really just one element called the linear harmonic oscillator, or the LC circuit. So we will review it in great depth and set it up in a way that makes bridging the classical to the quantum easy. Then we finally get to quantizing the oscillator, so we'll see wave functions. And then we will actually write down the wave functions and the energy levels and the control of a real transmon qubit. And this is our adventure for today. Why is this adventure important and why is it useful? Because for you to get to, one more lesson, or message. We will cover the theory and the underpinnings. However, you're in good hands because a lot of this is automated these days. And you'll hear a lot of different automation open source softwares throughout this workshop. I will focus on one that I can speak to that feels a lot like my baby, which is Qiskit Metal, which will automate a lot of the design of these processors and chips. It's an open source Apache 2.0 very permissive license. We'll have an advanced talk today at 4 o'clock where I'll cover more of its features and what we use it for. And in fact, it will allow you to take all of these abstractions and automate them. So here today, you learn the theory, but tomorrow you'll do the practice with Murat and the rest of the team. And if you want tutorials, there's quite an exhaustive tutorial page on the website here with all kinds of different methods of analysis. That should hopefully allow you to do things like these folks. I see Ben is here in the audience. Thank you, Ben, for sending these slides. So these are not my slides. I can just luckily report that other people, like for instance from this Niels Bohr Institute, have actually created a lot of very cool and interesting designs in Qiskit Metal and actually fabricated these in real life and built these chips and devices, which you can see here. Honestly, I don't even quite know what these structures are, so maybe you'll tell us afterwards. And in fact, you can begin to build these full chips yourself, hopefully after this workshop. fact, we're trying to make it as easy as possible. I'll mention other folks who have gone through this process and will also contribute to you today. You'll see here some of our organizers and presenters who have done some beautiful work and also cooled down and measured these devices and published a number of papers on them today. So thank you, Eli and Satman and everybody else here. The list goes on, actually. I think Figen might be with us virtually in the audience today, but this is an example on a Fluxonium qubit, analyzing and building Fluxonia qubit. There's more examples of more complicated chips as well, and all kinds of different devices and measurements. This is still a transmon qubit. It's now a circle instead of an X or a square. So my message here is just that everything we're going to study that looks a little abstract is actually used and automated, and we can begin to leverage it. But to know what you're doing, these are going to be the fundamentals, the one-on-ones that you really want to understand, because they will show up again and again and again, and everything else just builds on top of them. So that is why we're going to start from the beginning. Any questions? Okay, wonderful. So taking this huge step back, I'm not going to assume that you're a physicist. I assume there are all kinds of folks in this audience, electrical engineers and so on. Allow me to go back to the origin of why we're even talking about this. In fact, anytime you look up at the night sky on July 4th, you see a lot of fireworks. They have colors. Those colors directly represent the quantum nature of light. In fact, you can understand which you're doing NMR spectroscopy almost in some sense, or well, maybe then not NMR spectroscopy. You're doing a kind of spectroscopy where here's a sodium, which is yellow, here's a barium, which is green, and so on. So why do the different atoms have different colors? In fact, this is how quantum physics was discovered. Atoms are quantum, and one piece that means is that they have discrete intrinsic energy levels. So the energy of the atom, we like to say, can only be 0 or 1 or 2 or 3, but nothing in between when you measure it. However, you notice these energies are not spaced equally. The difference in the energy of two levels gives you a frequency. And that frequency is exactly the emission spectra, or the emission color, the color of the light that a photon, say, going from the level 1 to the level 0 will emit. And because these atoms all have different energy level structures, they all emit light at different colors. So if we make this a little more scientific, the atomic potential looks like this 1 over R potential here. And you can talk about the quantization of energy as a function of the radial distance of an electron from the atom. We don't need actually all those details. All we need to know is that there's an energy potential that looks like this. And I can fill in with quantum theory the different energy levels of that atom. So each red line here means that the atom can be at that energy. What you'll notice, however, is a few important observations. These are foundational. First is, this is anharmonic. All that means is just that these two levels don't have the same gap as the next two levels. The levels get closer and closer together. So when we shine a laser, or when we shine light and try to control this atom, we see that if we put a little red arrow that starts at the 0 level, and let's say it goes to the first level, it will move the atom from the 0 level to the 1 level. But when the atom is in the 1 level, this same laser cannot move it to the 2 level because the frequency is wrong. You lack that selectivity. You can only move the atom from one level to the other if you're on resonance typically. So that's how we get a qubit. There are no qubits, by the way. That doesn't exist. There are no two-level systems in the real world. They're really purely an abstraction. The atoms always have higher energy levels. We just tend to restrict our attention to the lowest manifold of two levels. So the level diagram allows us for qubit-specific control and readout. You notice that the atoms tend to be very isolated from the environment, especially when they're in a gas or just floating around. They're very low loss, meaning they retain their information for a long, long time. and they have many levels. All of those observations are going to translate over to the world of electrical circuits. We're going to take these one for one, going from real atoms to what we like to call artificial atoms, because we will engineer their electrical properties to mimic those of the real atoms. And the two fundamental building blocks are the capacitor and the inductor. Now, the problem is that in the classical world, we typically have linear elements, capacitors and inductors. And so when we build a energy potential out of these two, what we end up with are quadratic energy landscapes, with quadratic potentials, which have quantization that is harmonic. So we call it the harmonic oscillator since it oscillates at one frequency, just like the pendulum at low amplitude. And you notice that now when you try to attach an input-output wire to shine light, in this case typically microwave light, at the artificial atom, we cannot selectively isolate the lowest two energy levels. So the fundamental first unit we need to introduce in electrical quantum circuits is the idea of anharmonicity. We want to break this degeneracy. We want to be able to address just the lowest two levels without addressing the higher levels. And to do that, we typically make these inductors nonlinear. And it's not the only way, but the best way we know how to achieve this is through a Josephson tunnel junction, that little tiny element at the nanoscale that you saw in my earlier slides. So here we can see that a Josephson tunnel junction potential will actually very gently open up and soften the inductor. And so you get a slight anharmonicity in the transmont regime. And so the second level is slightly off resonant from the frequency of the first two levels, allowing us to ultimately isolate it. So the layers of abstraction that we go through start at the idealization of a qubit. We go to an anharmonic oscillator, which then corresponds to a physical model of a junction, typically in a capacitor, which then itself has somehow to correspond to the physical layout. And in fact, this jump right here is the hardest part in the art of our field. How do you do that? And that's what a lot of these softwares try to also automate. And then, of course, once you have a physical circuit model, it still can be challenging to understand all its properties. And that's where Jens and SE Qubits are going to tell us how to achieve that. In this lecture, we're going to focus mostly on the bridge between the physical circuit model and the anharmonic oscillator, which you could say is the bread and butter of circuit quantum electrodynamics, or CQED. It rests on the idea that there are two kinds of physicists: those who believe all of physics are spins, and those who believe all of physics are oscillators. After this lecture, you will have no doubt which one I am. So what are the building blocks? We saw this picture of the IBM chip earlier with microwave oscillators. That's really all these two structures are, this readout and this qubit. They're just oscillators. In fact, they're all made of just 4 components. The whole chip, that's it. They're just 4 components at the level of an abstraction. There are capacitive, inductive, and nonlinear inductive units, which are only the Josephson junctions, nothing else. Of course, other nonlinear inductors exist. We just don't use them en masse. And then there's also these transmission lines, which guide waves around the chip. You need a way to move your light around and feed it to different places. And in fact, it's a little bit like if you've ever been to a Mexican restaurant, you can get a burrito or a taco or a quesadilla, but it's all the same ingredients. They're just packaged differently. So we pretty much have, if you want, the same recipe in superconducting quantum circuits. We package up different meals, depending on whether you have a capacitor inductor or junction and capacitor, or more ingredients tiled in different ways. So all the chips you see online from Google, IBM, and so on are just made of diagrams like this. These are our Lego building blocks. So I'd like to spend a little time to introduce each of these and go through them carefully. You might ask, well, what the heck is quantum? I learned this stuff in middle school. There's nothing quantum about an LC circuit. Well, here are the things you need. This is why you can't do this in your home setup today that easily. First, you need low dissipation. These inductors and capacitors have to have very, very low dissipation. Second, you have to have isolation from the environment, so thermal fluctuations, the thermal noise. Third, you need typically low temperature for those reasons. You need a nonlinearity, otherwise everything is indistinguishable from the classical world. And finally, you'll see this slightly more nuanced idea that you need large vacuum fluctuations, large quantum vacuum fluctuations typically. We'll explain what that is. So that's the reason your microwave isn't quantum. Well, it is, but you just can't really tell. It's just plagued by thermal noise, dissipation, and it's also a linear system for the most part. That's why we rely on superconductivity, which has nominally no dissipation. It's typically got very low residual quasi-particle occupation, and it provides us with a very robust nonlinear effect, which earned Brian Josephson the Nobel Prize. Actually, quick fun trivia fact, I think I had to review a paper on the archive to see if it will be accepted, but from Brian Josephson, that's my claim to fame there. Okay. So where does all of this fit within the physical world? You can take a look at all the frequencies, or if you want equivalently temperature scales, to understand the regime we need to operate in. And we're going to do an order of magnitude estimate. Roughly all of the labs operate at about 10 to the minus 2 Kelvin, which is roughly here in terms of wavelengths and frequencies. Our resonators, the transmons, the readouts, operate at the range of about 10 gigahertz, 5 to 10 gigahertz, these days even less. That's a wavelength in free space of about 3 centimeters for a microwave, and it's roughly at the size scale of butterflies. So they're not really nanoscopic in that sense. And then, of course, atomic energy transitions, the visible light spectrum is roughly right here. There are many beautiful introductory reviews. I'll let you take a screenshot of this. So many written by authors in this audience. And if you want any of my slides, again, just go on the site. So if you feel like you missed anything, we'll share the slides later. Okay, now we start to dig into more of the meat. How do we go quantum? Well, first, we're going to start with classical, and we're going to go over the classical oscillator in some detail, but with a twist. So I'd like to start looking at structures like this, where you have a transmon qubit. It can have different shapes. For us, I'll pick this shape because it's the most commonly seen one. So what do you see here? Well, what you see is first this substrate. This is a dielectric piece of metal, typically silicon. You then see two metallic pads. I've taken care to add a little shine so you can tell it's metal. These are typically aluminum. Then you have this orange box. Here I've not taken care to really make things faithful. This is really just an abstraction. It looks like the video you saw earlier, but that's an inductor. Usually a Josephson tunnel junction. Now, the way you should think about this is that on these two metallic pads, there are electrons or holes, positive charges or negative charges that can move around. And in fact, think of these as a net charge, because there are many, many charges. There are billions of charges, and more than that. There are orders of magnitude of electron charges, typically 10 to the 12 mobile electrons in one of these islands. But the only ones we care about are the net charges. So that's quite a small number, quite frequently. So on one side, we can label all of them with a single variable called Q, which will denote the charge, the net charge on this piece of metal. And because of because they're connected, on the other side will typically have negative Q, where you have a different, the opposite net charge, if this whole island is charge neutral. This variable Q in classical physics goes between -infinity to +infinity and is a function of time. That's the oscillation. Now, what happens if I put charges and then I let them go? Well, you see, they're going to create they're going to pull on each other, and the charges from one side will try to flow over to the other side across the bridge. Because we've established an electric field, each charge creates an electric field, and these two, and so you have an electric field drop between the two plates. This electric field, which in principle depends on space, allows us to define a voltage. And so here I'll write V of t is the voltage that we can define between these two parallel plates. And we don't need to worry about what exactly it is. I've written how it relates to the electric field and the choice of a path you've taken from one island to the other, but we're always going to look across the bridge. So if you're an electrical engineer, this will make more sense. Otherwise, we're going to abstract this away, and you don't really need to worry about it unless you're doing a lot of HFSS. And the voltage also, it goes from -infinity to +infinity. The fundamental first constitutive relationship that is amazing in the sense that it works for any shape you have, whether it's a circle or a little piece picture like this of a qubit, is that the charge is going to linearly depend on the voltage across its two paths, at least as long as the structure is not too distributed. And this capacitance itself is, for all linear systems and physical systems, it's a number between 0 and infinity. And we like to represent it like this. So this is the first level of abstraction, right? We have a picture with metal pads. The shape could be different, but ultimately we're going to abstract it away into a simple box. And that's why, even though I showed you many different versions of a transmon qubit shape, in some level, the shape doesn't matter because you end up with a capacitance. Of course, there are details when it does matter, but that's more for the advanced track. They're really refinements. Because you have electric field, that's going to push charges. The charge is coupled to the electric field, and it will push a positive charge across this island, which will create a current being just the rate of the number of charges per second, if you want, that will pass through this current. So that's I of t, which will is universally related to the charge by this differential. So the rate of change of charge on the island we define as the current. And you can vice versa invert that relationship and say that current is the antiderivative charge. Typically in all circuit quantum electrodynamics, we begin with charge at time 0 or infinite negative time, if you want it, is set to 0. Just means we have neutral islands. We're not charging up our qubits with a lot of charge, as your experimental friends will tell you that's a very bad thing to do. And you see, there are different conventions. You have to be a little careful to make sure you define currents and voltages with the right sign. They're sign quantity. They're a vector quantity just reduced to one dimension. But the convention we will use and is always used to make the Hamiltonian and Lagrangian work well is to do this inverse relationship between current and voltage. So these are the little things that can trip you up if you do this on your own. Now, the variable that might be less familiar to you is what we like to call the flux, the magnetic flux across the bridge. So what does that mean? Well, really all you have to think of is that it's the antiderivative or the integral of the voltage. The same way the charge is the antiderivative of the current. It relates actually to Faraday's law of induction. So in fact, this relationship is universal. It doesn't matter if you have a linear, nonlinear, hysteretic conductor here. Whatever the element is, capacitive, inductive, etc., this relationship always holds. It's a fundamental law. there's maybe a slight point that Eli alluded to earlier, which is that, in fact, this flux or this magnetic inductance, you have to be a little careful because the Josephson tunnel junction can actually store energy in something called the kinetic inductance, not just the magnetic inductance, which has to do, magnetic inductance creates magnetic field lines, like you see these orange lines here, which are stored in space. That's a detail we'll get to in the second half of this lecture. And so finally, of course, the voltage is just a time derivative of the flux. Good. Any questions so far? Great. So the second relationship we need is that the magnetic flux is related linearly to the current through the bridge. And in fact, it's just L, just like the capacitance. It's a number between 0 and infinity. And we like to symbolize it with that little squiggly symbol. The final two pieces we need is to remind ourselves what power and energy are. So there's a universal relationship. Again, this doesn't care whether you have a nonlinear element or a linear element, but the rate of change of energy stored in a component is directly equal to the instantaneous power flowing through it, which is just the product of the current and voltage. And so you can write out what the energy is for these two elements. You can derive these from the constitutive relationships of the previous page. I'll let you work it out if you'd like. But really the thing to remember is that they are quadratic. You see that the energy of the capacitor is a function of, let's say, the flux. Well, the charge is Q squared over 2C, or as a function of the voltage across the capacitor is 1/2 CV squared, or 1/2 C phi dot squared. And similarly for the inductor. So when we talked about the quadratic energy landscape in the earlier slides, that's really what we were pointing to, is that this energy landscape is quadratic. In other words, the forces are linear. So that's why we call it linear. The forces are the derivative of these. Any questions? Okay. So to summarize our base and most kind of fundamental manifestations of electricity, we really have these four relationships that are universal. They always hold true no matter what kind of component you have. And then we link them with cross-diagonally like this with the elemental. These arrows that go diagonal depend on the actual elements we have, such as an inductor or a capacitor. And the Josephson tunnel junction will also go in here between the current and the flux. Good. Now, let's actually take the abstraction of this physical picture and turn it into an inductor and capacitor picture. This is the notation we'll use. The little open circle means that that's a node of the circle, and this little triangle means that it's a ground in the system. But let's walk through an example and it will become more clear. So first, each element in the circuit, so this is now quantization 101, each element in the circuit has its own voltage and its own flux. In this case, I'm going to use fluxes rather than voltages, as you'll see in a minute, but that's really the variable that makes life easier to work in. And similarly, I'll define a flux for the capacitor. There are really two types of quantities you have. There are these branch quantities, or three if you want. There are branch quantities that depend on the branch in this circuit graph. There are also loop quantities, things that depend on, let's say, the loop here that I have in this graph. And then there are node quantities that depend on the value of some variable at the nodes. And this goes back to Maxwell's equations and Kirchhoff's laws. Kirchhoff's law tells us that there's a fundamental relationship of electromagnetism at each node. At each node, we have to always satisfy that the sum of the currents is equal to 0. There's no accumulation of charge at a node. This is a conservation of charge fundamentally. Notice that there is a plus sign or minus sign because the way we define these currents for the branch, if you remember from my earlier slide, depends on the chosen convention. See, I could have defined this arrow reversed, and then I would have a minus sign if I write down the equations here. Then we have equations that we can write down for each node. In this case, there's only one single node. So I can say that the current on the capacitor right here, plus the current on the inductor right here, should be 0. And all of that's saying is that I have conservation of charge. If current from the capacitor comes into the node, the only place it can go is into the inductor. That's it. The other set of laws you have are Faraday's law of induction, which leads to Kirchhoff's voltage law. And that says that for every loop in the graph, if you sum the branch fluxes around the loop, again with a sign, be careful about the sign, you will always get 0. That's at least the traditional form. You'll see that in superconducting circuits, it can actually equal the external magnetic flux, but let's not worry about that for now. So let's do it in our example. If I take the loop 1, now there's only one loop, so you might ask, well, why the hell is Zlatko, putting labels on these? That's because I'm writing everything in the way that it would generalize to an arbitrary circuit where you have n nodes and L loops. That's why we're using this heavier machinery for something very, very simple. But the procedure we're going to do is exactly the same for a big graph. So for my one loop, or if I had many loops, I would do this for each loop. I now take the voltage of the branches in a sine way and say that it should be equal to 0. In this case, I take again, all this says is that the voltage of the capacitor should be the voltage of the inductor, which is kind of a trivial statement. In this case, that tells us that those two magnetic fluxes should also be the same if you integrate this equation. And that's it. Effectively, that's all that electrical circuits are. That's really all the equations. You've written down that once you take the constitutive relationships, you substitute in these node equations and these loop equations, and you put everything together, you end up with an equation of motion. I haven't done it step by step for you here, but effectively you can combine this and this using the definition of what a capacitor and inductor is. See three sets of equations, and you get an equation of motion, which is known as the linear harmonic oscillator equation. And really, that's all that circuit theory is. That's it. There's everything else is a consequence of these three things.
What's one question? Like where you put the minus there, is it like some right hand or left hand convention?
For the loop?
Yeah.
Yes, good question. So the loops also have an orientation. So you see how I've drawn the loop going to the right? I could have flipped it and made it counterclockwise. So if I had done that, it would have simply made this a plus and this a minus, because you have to take into, here the loop and the arrow of the phi c go together. But you see, if I follow the loop, then phi l goes negative, goes against. So that's why I put a minus. Good. Any other questions? Excellent. So I will go through this piece a little bit more speedy, but the idea is that everything you know about classical harmonic oscillators repeats. Since you guys are a super cool beginner audience, but slow me down if you need to, I will kind of walk you through it a little more rapidly. So you can solve for the harmonic frequency, the resonant frequency of this mode. You can solve this equation, define a frequency of oscillation. It's 1 over the square root of LC. It should look like what you learned in middle school or high school about harmonic oscillators. There's an equilibrium position of the spring, a mass on the spring. This is the analogy. At x equal to 0, which is the same thing as phi equal to 0, we call that equilibrium. Any deviation from this equilibrium is really what we're describing here. These equations are always written around the equilibrium position. So if the system is frustrated, yes, hopefully the video is playing okay for you. But, all we're describing with these equations is a spring and a mass system where phi dot, the voltage, is like the velocity. Now, how do we go to the quantum world where we have Hamiltonians? Well, typically you need to write down a classical Hamiltonian first, which involves writing down a classical Lagrangian. If you don't know what that is, I'll write it down for you. Now, it's actually not that hard. All it says is that you write down all the energies of the capacitors as a function of the voltage, and you subtract from them all the energies of the inductors in terms of the fluxes. That's all it is. It's just a functional of the energies of the system. So if you write down the Lagrangian, it's the kinetic energy minus the potential energy. What's kinetic and what's potential really depends on your choice of variables, but we will always work with the fluxes being our position variable, so to speak. And so we'll always write them like this. You can then define the canonically conjugate variable, which is called momentum, or in classical physics, but here it just becomes charge. It's the same thing as the electrical charge. And you'll notice, by the way, that all this says is that charge is the current, is the capacitance times the voltage. So in a way, we haven't actually said anything interesting or new. We've simply used some fancy symbols to write down the things we already knew.
Question?
Yep.
So I'm trying to understand the jump from just classical, just E and M to
Yeah.
the lumped element stuff, and what's lost in that process.
Oh.
Because presumably everything we're doing here we can just do the Maxwell Lagrangian and essentially in principle do that. But
Great
Yeah.
question. Yeah, so the question is, we've gone to just two variables from showing you a picture that had a whole distributed structure. So what did we lose in the process? And this is a great question. We're abstracting away 99% of this structure. And the beautiful thing is that 99% of it in a way doesn't matter very much, because in circuit quantum electrodynamics, we're typically interested in the low energy excitations, really the main modes, the fundamental modes of this structure. Of course, this structure could have weird high frequency modes and so on. But the only thing we need is an effective description of the oscillations of the currents and charges of these two two islands in the inductor between them. So we've lost all spatial information, which is very important if you want to optimize noise in the system. So maybe you know that your dielectric has some kind of lossy mechanism. Maybe you know that if you have a sharp corner that creates a strong electric field, and then that couples strongly to two-level systems. So all those kinds of details that you would optimize in a real quantum device are lost. We're really just describing the effective dynamics of one mode. If we wanted to make two modes of the system, we could add one more LC circuit and couple them. So in fact, you can make this picture increasingly complicated. Might call this a white box model, to capture more and more of the dynamics and even spatial configuration of the physical full system. So with transmission lines or CPWs, you might write down an infinite chain of LC circuits to describe, kind of the continuum space, but it's a one-dimensional LC circuit infinite ladder as opposed to the three-dimensional, like coplanar waveguide, for instance. Does that help?
yeah, so I'm just gonna
Yeah.
basically integrate all those extended things to a compass. That'll be how I get from one picture to the next.
Yes, how you actually, right, so how you go from here to here, it's one to many. There are many different LC circuits that would all give you the same resonant frequency, because you notice that the resonant frequency was 1 over the square root of LC. So L over C is undefined. So in a way, we like to say that there are many different effective impedances you could choose, and they depend on where you look. Oftentimes, we'll choose the L and C in such a way that they represent what it would look like to couple to the system right at the junction site. But that's not the only way you have to construct it. So there's a degree of freedom. There's a gauge degree of freedom of what you choose as your L and C, and there's a kind of procedure you can use to try to set that. But eventually, Kiskett metal, energy participation ratio, black box quantization, if you've heard of those methods, they all kind of figure out effective models to give you these parameters, or they just skip these parameters altogether and give you the answer without them.
Thank you.
Good. Any other questions? Okay. Great. Okay, so in the interest of time, let me just give you the high-level picture on the Lagrangian equations so we can get more to the quantum side. Essentially, you follow very standard mechanics, and you can write down the equivalent of F equals ma, called the Euler-Lagrange equation, which will amount to just writing down the equation of motion we wrote already on the earlier slide without the Lagrangian. We didn't need the Lagrangian to write down these equations of motion. The reason we needed the Lagrangian is at least to formally make the move from the circuit into the Hamiltonian. And I only want to illustrate for you kind of the proper sequence of steps, because most of the time you're going to skip these and just, you could have written this down at the beginning of my slide where I said the energy of these things is this. But in more complicated circuits, sometimes things get tricky and you have to actually walk through every step of the Lagrangian to not get things wrong. Okay. So there's a beautiful analogy between the classical harmonic oscillator for a spring and mass system and an LC oscillator. It's sometimes useful to think of a mass and a spring. Oops. Let's see. And so at the end of the day, the thing that we will care about is to say that the classical Hamiltonian is a function of the magnetic flux across the inductor and the charge that's dual to it, which is just the charge on this node. And it's a quadratic function, both in the kinetic energy, Q squared over 2C, and the potential energy, which is phi squared over 2L, where the frequency, omega naught squared, is 1 over LC. And then the impedance, which we'll define as Z0, is L over C. So to the earlier question, omega naught is very much fixed. You know, the distributed structure has one resonant frequency. There's no question about that. But what you define as the impedance, it's an open question. It's a gauge. You can choose different gauges. So if you plot the magnetic flux on the bottom and you look at the energy landscape of it, if you want to think of this as a classical particle, the classical particle can only be on this black line. It can never be in the shaded region, and it can just oscillate back and forth like this. You know, it's by logic that we prove, but by intuition that we discover. So we've done a lot of math, but maybe it's useful to just give you a picture very quickly of the dynamics, and then we'll take a break. So if our Hamiltonian, which just tells us the energy in the system, is a quadratic function of the charge and the flux, let's make things simple. Let's say L is equal to C is equal to 1, right? Just to make the picture really easy. Then we can say that the energy is 1/2 Q squared plus phi squared. And then if you want to go to the quantum world, you might say, well, why don't I just set this equal to h bar omega naught times the number of quanta of energy I have. This is a kind of semi-classical picture or treatment. And you know, you can even try to be clever and add in an extra vacuum fluctuation of 1/2, because you know, if you've ever done quantum mechanics, you know that this is the energy of a quantum harmonic oscillator. So right now, this is completely hand-wavy semi-classical analysis, which we'll do it more precisely in a second. But if I do that and I draw for you the lines at different number of quanta of energy n, you get a phase plot that looks like this in the flux charge picture. So all this says is that if the particle had no quanta of energy, it would live and move and oscillate on this ring right here in the center. If it had 1 unit of energy, it would oscillate and move on this ring right here, and so on. And so what does the classical trajectory look like, or the classical equations of motion? They look like the, again, I could phrase it as the Legendre equations, or you know, the phi dot is, the Hamiltonian equations of motion. So the voltage is equal to the partial derivative of the Hamiltonian with respect to the charge and vice versa. These are really F equals ma equations. And so the classical particle would simply rotate and oscillate along this trajectory like this. And so this allows us to define a variable, sometimes called the action angle variable, that allows you to exactly track the circular motion of the particle. You see this alpha of t. And if you had a L and C that were not 1, you would write some normalization factors, but effectively you can just write this classical complex variable that all it's doing is tracking where the particle is in this plane. Okay. And it depends on the flux and it depends on the charge and has some scale factor. And if you want to describe the evolution of the harmonic oscillator, it's very easy in this system because all you have to say is that this complex variable recesses or rotates at the natural frequency of the harmonic oscillator. And it just does this evolution. In fact, you'll see that this alpha is what we will use to describe all the quantum evolution in a minute. It will be the classical equivalent of the raising and lowering or A and A dagger operators in the quantum world that Eli showed many examples of in the slides. And we're going to get to that in right after the break. So I think this is a good time to, yes, so maybe in the final slide, I'll just say you can now rewrite the Hamiltonian, even at the classical level, in terms of this action angle coordinate system, or these this complex variable alpha. So far, it looks like I just did a manipulation of variables because in a way, that's all it is. But in the quantum sense, it will then be very natural and easy to write down the Hamiltonian exactly in this form, where we simply replace these alphas with ladder operators. So this is a great time to pause before unveiling quantum and take a 5-minute break. Maybe one question first, and we go to the break.
So you ignored the resistance in the circuit. So is this because of the superconducting nature of the circuit, or and how, like, if you run the system for a long time, there will be some heat dissipation?
Great question. The question is, what about resistors? I never put a resistor in my slides, if you noticed, in my building blocks. In a way, they are there. Maybe we should include them as building blocks because they're unavoidable, but they're really the imperfections. And I'm giving you the idealized picture. Even if you had a classical circuit that had very little dissipation, well, all circuits are quantum ultimately. It's just there's usually too much thermal fluctuations and too much dissipation. I mean, those two go hand in hand. So I'm giving you the ideal picture for a superconducting circuit with no dissipation. Okay, let's take a 5-minute break, and you guys can come and ask me questions. Yeah.
This first, and I don't know what's it called. Education. I just found out all the.
Yes, I haven't put these yet.
Okay.
But a very similar slide.
That's what I thought.
I did easy for
Oh,
the students could all
very early slides show that the linear harmonic oscillator, they are equally spaced. So let's see.
If they don't continue, why are we getting
Within the first
spaced?
Yeah.
These corresponds to this, right? Why is it not?
Purely classical.
Yeah, earlier. Can you compare the harmonic kind. Yeah. Slightly. Here, why are they increased?
Oh, yes, yes. So I haven't shown you that frequency. Yeah, I saw it, when I said that, like, in the last lecture where I had this one Q squared over 2 C plus pi squared over 2L equals like H bar. So that H bar over, so that this is exactly that.
Oh, like how do you
H bar. Yeah, like.
Okay.
Yeah.
Why are they equal?
So I don't know the really rigorous resources. It's not a rigorous procedure. You sort of guess that. The way we do it,
Here also,
the way we actually sort of
y-axis
do it
has to be, sorry, the x-axis has to be the
and then we write down the radius and say like, okay, that's going to be this way.
But when the radius don't, the energy will be so
like we know there's going to be capacitor between these two elements. There's metal that's near it. What we don't know is what if it's so we can draw, range between those two levels. And then we use this
so the energy will be very
to solve for what so that's this numerical simulation. That's using the full structure. And Arad and Chantal will tomorrow and workshop and show you how to do it. But things aren't finite. Things aren't zero sum. So you're making it like an assumption. So you just know yes, that's one thing. That's not true. So that's like an approximation. And so it may be the case that what you find. Now there's ways to check. One thing you can do with selective optimization is directly solve the eigenmodal simulation. Basically just tries to like excite the system frequency sort of note that it seems to respond directly from that. And we can say like, okay, does that agree with what I think the modes are? And if those don't agree very closely, then you know. Either that you can spend your simulation, but often you might set up a graph that you are missing a branch, or that you are treating something as a lump element that you really need to treat as distributed. And we distributed elements is by treating them as an effective lump model, but you can say that.
So you can always find a way to lump it. You just
So this is something my lab's actually working on a little bit right now. One of my you have the transmission line. You can model a transmission line infinite series of LCDs. But it's really hard to write down an infinite series in paper. And so the question is like, okay, how many do you actually want? Can you get away with 5? Do you do just LC, 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 LC? Is that enough? Or do you need to do 20? And because every time you add a node, it gets more.
Sorry, I kind of rushed at the end.
Do you want to use this tool?
Break base.
Justin's like this
So, yeah, please interrupt me with
pet project that I think he's wanted to do for a while, treating the full transmission
So,
line as a.
This is purely heuristic. It just says.
Yeah, no, I mean, so, okay. Jens is the guy to talk to about this. Like, how do you correctly set up the graph?
So what if I just like. What if I say that, in principle, the particle could be anywhere in this plot, in the classical world, but we know, if the energy of the particle depends on the radius, because it's q squared plus pi squared, that's basically the radius of this plot. And so I could say, well, what if I can only have energy that is units of a single photon.
Let's check to make manipulating
Yes, by saying I can only have energy in discrete units of H bar omega naught. This is actually what you find in quantum physics. It started here.
It's in between the circuit diagram, but it really it is exact in the graph. In the sense of like it has nodes, it branches. It turns out that for really complicated stuff, graph is really
Yes. I'll go over this.
How do you?
Maybe I should.
Oh, no, you just write down.
I think it's one over R squared. Yes, I'll explain this, a second. Yeah, we'll get to that. Yeah. And that can The next part. He was given the Oh, yeah.
He is, yes.
Okay. All right, guys, I think we're ready to,
It's hard.
all right, guys, I think we're ready to get back to it. Okay. So I think we figured out the lights, so thank you. Now, somebody asked me a question during the middle of this break, which was, we kind of rushed at the end and went to this quantization. So why did you take the classical harmonic oscillator and really say that the energy should be in discrete units? And just to go back to the original picture of quantum mechanics, the energy landscape between an atom and an electron. The atom, the nucleus is usually positive. If you have one proton and you have one electron, they want to attract and they actually want to come together because they're charges of opposite parity. So this energy potential here represents that. So if the nucleus is fixed and the electron starts here, in a classical trajectory, it would just walk down this parabola and fall into the nucleus, and they would fall together into one. But in quantum physics, we found out that the electron doesn't actually spiral in and fall into the nucleus. It always stays apart. And why is that? The reason is, well, you could say it one way is that there is a minimum energy of the electron that is given by quantum mechanics that is quantized. So there is an absolute minimum that's not zero, it's larger than zero. We kind of like to say the electron has to fluctuate. And that's this energy level here. And then in the light spectra, the fact that you see the discrete lights in fireworks tells you that you have a gap in energy. You can't have any energy. The particle can't be anywhere on this parabola. It can only be here or here or here. So what we tried to just do in the classical harmonic oscillators to do the same intuitive picture and just hand wave and say, there must be a minimum energy. I'll call that H bar 0. And then the next energy levels, let's say that they come in discrete lumps. We know that discrete energy levels is a key feature of quantum mechanics. So let's just try to do this semi-classically. And that's how we ended up with the nice picture where we took the potential of the classical harmonic oscillator and we wrote down a completely unjustified equality, which says that there must be a minimum energy, 1/2 h bar omega naught. which corresponds to a particle that is on this trajectory right here. And in fact, the particle in the classical world can have any charge and any flux, but if we quantize the energy, then it cannot. It can't be here or here. Let's say it must exactly live on this line, or this line, or this line. That's if you take it in discrete lumps. So this is quantization, more or less as the founders of quantum mechanics started out. Now, soon they found out that this actually gives you the right answer, but it's not really the right procedure. And so, in fact, they needed a better procedure to bridge any classical Hamiltonian for any atom or circuit to the quantum world. So that brings us to unveiling the quantum. We're going to start with the quantum harmonic oscillator, and we're going to bridge from the world of classical physics to the world of Schrödinger castle. I won't spend too much time on this, but if you do want to know, there is a formal procedure called Dirac's canonical quantization, which works in many cases, where you basically say that on the classical side, we could write down the Hamiltonian equations of motion, and there's something called a Poisson bracket. And pretty much this procedure is to supplant or to replace this classical Poisson bracket. If you've never heard of it, it's just know that it exists with a commutator, a quantum commutator of the operators. And then you insert an I and an H bar. You might ask, well, how did you figure that out? And the answer is this is really, this is a postulate, if you want. This is a method that's quite general that Dirac came up with. And in fact, it's what we do in circuit quantum electrodynamics a lot of the time. The truth is, this method is not valid. It breaks down in certain cases. So if you want to know the more true method, which only was figured out about 100 years after, ask Michel Devray. He will tell you the sort of the more proper way to do this. But if you look at a lot of the field and the way that we do quantization in our superconducting qubit field, we tend to just use this procedure where we write down the classical Hamiltonian, we write down the canonical position and momentum, and we supplant their Poisson brackets with a quantum commutator like this. And this is the bridge from the classical world to the quantum world. I just want you to know that there is a formal procedure, and in fact, there's an even more proper way to do this, but that's all you need to know for now. You might ask, this sounds fishy. Sounds like you don't really know what you're doing. And I like to think back to Albert's quote that if I knew what I was doing, it wouldn't be called research. But anyway, this procedure has worked quite well. So coming back to the analogy, in fact, that's in a way how we're going to bridge these two worlds. We're going to make a bridge from the classical to the quantum. So in the classical world, we have a function, the flux at time t, which we are now going to replace with an operator, a quantum operator denoted by this hat. The time has dropped because we're in the Schrödinger picture, not the Heisenberg time evolution picture. And you do the same thing for the charge and for the classical Hamiltonian. You now write down the quantum Hamiltonian. You do this trick with the Poisson bracket replaced. So that tells you that the commutator between the flux and the charge is exactly IH bar. And most importantly, if you take the action angle variable alpha in the classical world with its complex conjugate, its Poisson bracket is supplanted and becomes, these operators become exactly the A and A dagger or raising and lowering operators, which you will see a lot of in the next slides. Because these are the operators that allow us to go up and down the ladder of energy levels. Good. Any questions? Okay. And this is what I mean by commutator and Poisson bracket, if you really must know. So on the classical side, we could write the Hamiltonian either in charge and flux or equivalently in action angle variables. And on the quantum side, we could write down the exact same expressions simply with the symbols replaced by little hats. That's it. Any questions? Yep.
So my question still remains, we are only able to do this translation when we ensure that the energies of this classical Hamiltonian are quantized, right?
You know, that plot I showed you with the circles and setting things to E equals 1/2 h bar and so on. This was a kind of heuristic way to just draw a picture of what would happen. But you don't need to do that. It's more or less equivalent. There's a slightly more formal thing where you talk about the area in phase space, and you talk about the amount of action contained in that area. And then you can quantize, we actually quantize based on action, not energy. So it's basically the area, and that allows you to do nonlinear oscillators as well. But for this lecture, that was more of just a picture to try to get you some intuition, as Henri Poincaré said. It's not a strictly speaking formal picture. Thank you. Good. Any questions? Okay. Then you have things in, let's call it phase space, for lack of a much better word. You know, on the classical side, again, you can define this action angle variable alpha, which just tells you where the oscillator is. It's just rotating. The reason you have these extra factors is they're just scaling factors for the ratio between the flux and charge. But it's that circle picture. This is why I'm trying not to get you lost in just abstract algebra, but put a picture to you. This is the point on that circle. And in the quantum sense, you have more or less the same thing, this red ladder operator. And guess what? The equations of motion are identical on the classical side and quantum side. So on the quantum side, if you want to write down the way that this operator, the lowering operator, evolves in the Heisenberg picture, it looks exactly like what you would have written down on the classical side. So that's why we spend so much time on the classical side, because most of this quantum, like 80% of quantum circuits looks very much like a classical circuit. And then there's 20%, which is truly quantum and has no analog. But I found it very, very useful to think of classical circuits. And ultimately, you can also write down a very, very useful and fundamental way to express now the flux and the charge in terms of these action angle variables, or equivalently the flux and charge in terms of raising and lowering operators on the quantum side. And quite often, when you do circuit quantization or you think of quantum circuits, you actually just start here. You skip all the steps we've walked over. You know, you should know what they mean and how to get here. Quite often, people will just start at this framework where you write down and expand these fluxes in terms of these raising and lowering operators.
Yeah. Normally, when I think of a quantum state in, like, for instance, flux space, there's like a distribution of phi, right? If I now go away from the Heisenberg picture, do I have to imagine that this time evolves, like a ground state, or
the A operator?
Yeah.
Yeah, that's why there's different pictures and they're all useful. So there's a picture in which you think of A as evolving and rotating. In the Schrodinger picture, of course, the state looks like something. And, you know, the closest thing then to talk about representing is the Q function, the Beginner function. Let's say the Q function. So if you looked at the Q function of so-called Q function, it's a picture over phase space. It looks exactly like you put a fuzz around each of these lines. And so you can actually say that these lines are the semi-classical average trajectory of each. Anyway, maybe it's getting too detailed.
Yeah, okay.
I'm not sure I answered your question. Hopefully it got closer.
What's the subscript ZPF?
Good question. Thank you. So why did I put a phi ZPF? You see, all I did here is say that this flux operator is just a linear combination of the raising and lowering operators. Phi ZPF is a constant. There's no reason why I should have put ZPF at the moment, other than I have some foresight. And my foresight will tell you that this variable here, this parameter, it gives you a miraculous quantity. It in fact tells you what that fluctuation is, you know, in the ground state. It tells you how much the quantum vacuum fluctuations, or the zero energy 0 point fluctuations, that's like 0 point fluctuations, ZPF, the 0-point fluctuations that the flux operator are. If you go back to our atomic picture, we said the electron can never fall into the nucleus. Why? Because it has 0-point fluctuations. Because even at the lowest energy, it's fluctuating, and there's a standard deviation, there's a radius of that fluctuation. That standard deviation of that variable is given by this quantity phi ZPF. So it tells you how much, even in the ground state, the variable is fluctuating. I have pictures on this in a few slides.
Does that correspond to vacuum fluctuations?
Yes, yeah. These are the vacuum fluctuation. It's the standard deviation of the vacuum fluctuations of the flux operator in the ground state. And there's a picture in a few slides, but for now, it's a value that will be very key. In fact, you'll see that this value is going to determine most phi ZPF and QZPF will determine almost all the properties of the transmart qubit and its coupling to other systems. So if you have more questions about quantization, Michel Devoret is right there, and you can really ask him about canonical quantization. Excellent. So let's see where we are. So maybe we should remind everyone what these raising and lowering operators are, just for a minute. So you know, in quantum mechanics, we write each energy level as a little ket like this, where we say this means that we're in the 0 energy. And you see a lowering, this A, I'll just tell you, the lowering operator will destroy or annihilate that 0 ground state. So it just gives you nothing. If you're in the 1 state, it instead lowers you into the 0 state. It's kind of hopping up and down the ladder. Vice versa, its Hermitian conjugate, or its dagger, A dagger, acted on the 0 state, will transform 0 into 1. And likewise, it will transform 1 into 2, so on, with a little scaling coefficient that depends on in general, on how many photons are in the oscillator. So there's a beautiful image in DJ Griffith's book of these ladder operators simply allowing you to go up and down the energy ladder with some coefficients. In fact, they're very important that they're square root of n and n+1. If you are more of an electrical engineer or a computer scientist, maybe you don't want to think about ladders, you just like matrices, you can write equivalently all of these just as matrices. So in fact, they don't look that scary because they're mostly zeros everywhere when written in the energy basis. They're just off diagonal. And if you take the product of A dagger A, you can probably do this matrix multiplication in your head. And you notice that A dagger A, in fact, just gives you a diagonal matrix that says 1, 2, 3, 4. You see, it just counts what energy level you are at. Should I think Michelle has already caught a typo in my. Thank you, Michelle. So. Yes, Michelle's correctly pointed out, I've written down A dagger. So this gives you hope because you can clearly do matrix multiplication better than I can. Thank you, Michelle, for catching that typo. That is indeed a typo. So let's come back to the picture. You know, we've done some equations. Let's come back to some visual pictures and build some intuition. Let's go back to what we started with, this energy landscape picture in the classical world, where we say, let's describe the oscillator in terms of its flux variable, or phi. In the classical world, the particle has to live on this parabola, right? Because if it's at this position, its energy must be exactly this value, phi squared over 2L. So what happens in the quantum world? Where we can plot the so-called wave function, which just means that it's the overlap. Well, it's the wave function that will tell us a little bit about the distribution of what this flux variable is doing, or the particle is doing, if you want. And we said in the ground state, in the lowest energy state, first, the energy is not 0. And second, there's a probability of finding the variable phi, of the LC circuit in a non-zero state. In fact, there's a width to it. There's a kind of Gaussian distribution over which you can measure the flux. So if you want the particle is fluctuating, the electrical circuit, even in its ground state, has some voltage and current fluctuations. And in fact, it can protrude into the, let's call it classically forbidden region. And we can go up and up into higher and higher energy levels, and you'll see that they take some particular shape, and there's oscillations. It looks like wave mechanics. I've here offset all the wave functions exactly up to their energy level, with there, you'll notice they're evenly spaced, up to a factor of 1/2 of the quantum. Good. So maybe let's just pause. Is there a question on this slide? To answer your question from earlier, what does phi ZPF mean? Phi ZPF is precisely the width of this Gaussian in the vacuum state. It tells you how far the particle excursions are even in the ground state. And then the width of each subsequent energy levels are also determined by the scaling factor phi ZPF. Yeah,
So does this intersection into the classical forbidden region have some consequences? Does that refer to something?
yes, it will. In fact, Michelle and Jens did a lot of the original work, but you see that when we have a transmon qubit in the Josephson tunnel junction, there will be a cosine potential, and these excursions can in fact allow a particle to hop over the potential, even or maybe find its way into the other well in certain situations, when otherwise it would be forbidden, and that causes very important effects in quantum circuits.
Let me really, what is this phi? This phi cat thing? What is it? I can say that.
Great. I specifically kind of swept that under the rug, but this means that we have an eigenstate of the flux operator. So this is an eigenstate of the flux operator. It's a dual of the eigenstate of the flux operator whose eigenvalue is phi. So in other words, that looks like, if in this picture, it would look like a delta function at the value phi. It's just the formal way to write this decomposition. I could have written a Q there, and then we would write this picture in the charge basis, but it looks basically the same.
Can I maybe ask my question again now?
Yeah.
Because in your previous picture, you had kind of a closed motion in phase space of phi, right?
Yeah.
And now you have a probability distribution of your phi.
Mm-hmm. Yes.
I'm just trying to make the connection.
Yes. So now it's a one-dimensional plot instead of a two-dimensional plot. And in a way, you can think of it as some projection onto one axis.
Mm-hmm.
And so you're really just seeing the slice of the Gaussian and the ground state from one angle. This space, so you have all the information in the flux spaces, but you don't have the information of what's happening in the charge basis.
Yeah.
So that would be a more complicated picture. In fact, if you'd like, maybe I should just show you this since we touched on it. Can you see my slide? Yes. Good. So to answer your question a little bit more completely, then I probably have to show you the this picture, which is the phase space picture. So now we're taking an advanced bend. So, beware, dragons live here. In the classical, semi-classical picture we looked at, we said that the particle can live at a fixed energy. It lives on a circle and just rotates around like this. So what about the quantum particle? Well, you see, you can write down something called the Buscemi Q function, which tries to depict where the particle lives, the probability of finding the particle more or less. And in the ground state, you notice that the same plot, the phi and Q plot, looks like a Gaussian, 2D Gaussian. So most likely you'll find the particle at 0, 0. It has no flux and no charge, but it has fluctuations. In fact, it can have some flux and some charge. But in the one state, in fact, you will never find it. Well, you will very unlikely find it with 0, 0. You'll find it, in fact, right around that first line, but fuzzed out. Why? Because there are fluctuations. So in fact, it looks a lot like the classical picture. You simply made it a fuzzy picture. You just jiggled it around. Because in quantum, we have these 0-point fluctuations. We have fluctuations, things jiggle. You can't simultaneously know the position and momentum at the same time. And that leads to this kind of fundamental fuzz.
It's still more of a probability distribution in phase space, not really like a motion thing, right? Or
Yes, these are average statements, right? You can, this is an average statement. If you try to ask, is the particle at x and y at the same time, or at x and p, right? Get into,
yeah.
Yes. Good. Okay. Oh yeah, these were pop-up questions that I skipped. So, oh, okay, thank you. Okay, so I think that takes us to the transmon. Good. Okay, so, okay, maybe we'll, I lost my slide. I think the next thing we'll do is, now that we have covered the harmonic oscillator in quite some depth, actually right here, let's finish this. This is really as much as I would like to say about the quantum harmonic oscillator. And now we can actually, with not that much energy, do the transmon qubit, because you see that, you know, this last hour and a half of looking at classical harmonic oscillator and quantum harmonic oscillator, which may seem very, very simple and trivial at first, is really all the foundational building block knowledge you need to then begin to treat all the advanced systems, because they're going to use the same ingredients, like the picture of the burrito we thought of earlier. Okay. So this is a summary I'll just throw up if you need a summary of everything we said about these classical and quantum harmonic oscillators. I don't want to walk through it again, it's just a summary. So let's go back to our original picture of the distributed oscillator, where we now replace the bridge with not a linear inductor, but a Josephson tunnel junction, a nonlinear inductor. So what does it look like? There's a beautiful image by Luigi Frunzio at Yale University, which shows you in great detail how one metallic island is impeded upon or intersects with this other metallic island of aluminum, top of silicon here. And in fact, everything we will want to study and say is going to be about the interface between these two pieces of metals separated by a little oxygen barrier. This picture may look incredibly scary and dangerous, and how do you describe all the physics? But the amazing thing is that at the end of the day, the only thing, this is such a robust construction that you can abstract everything away, even all this little granular pieces here. You can forget all of it and just write it down as a single element with two nodes and a little x between it, called the Josephson tunnel junction. We can describe all of its dynamics in terms of a single variable called the generalized magnetic flux across the junction. So I'll use a sub j there to note that it's the junction. And this was a Nobel Prize, right? It's energy functional, Ej of phi j, this means energy, is just some constant called the Josephson energy, B sub j, times 1 minus the cosine of the reduced magnetic flux across it. So it's the magnetic flux phi, which we introduced in the beginning. That's just the integral of the voltage, renormalized by some fundamental constant called phi naught, which is h bar divided by 2e. For our purposes, and for most circuits we'll look at, in fact, you take a hair comb and split terms in two sides. You can split them into a purely linear piece, because that's what we just spent an hour and a half dealing with, so you know exactly what to do. I don't need to teach you more there. And a nonlinear piece, which is the only modification we're going to take. So if I go back to my middle school books and look at what a Taylor series is, I can Taylor expand this whole function and break it up into a linear piece, which is exactly quadratic, which is Ej over 2 phi j squared over phi naught squared. harmonic oscillator, and a nonlinear piece, which to leading order is negative EJ over 24 times the fourth power of this flux. Or as Michel likes to break this down or up, depending on how you think of it, likes to break up the junction into different terms. So you can think of the linear piece as looking at like your inductor, and then in parallel with it, you have a fourth order nonlinearity. So you get this kind of shaped symbol, the spider, and you can go to higher and higher terms. You have to be very careful here in the picture decomposition that this holds. So what is the transmon qubit that we've heard so much about? Well, it's the harmonic oscillator with a minor modification where you replace the junction, the inductor by junction. So now instead of an L, you have an EJ or an LJ. They're the same thing because you can effectively relate them. You remember how we wrote down the energy of a capacitor? That stays the same. The energy of the inductor is replaced by the energy of this transmon qubit. You might ask, what exactly is phi naught? Well, it's roughly 3×10⁻16 febers, so it's a fairly small number. And then what does the energy landscape, the potential energy landscape look like of this picture? Well, now instead of a simple parabola, you see a cosine. And in fact, to first order this cosine, to leading order in the Taylor expansion, this cosine looks like a parabola, just like our harmonic oscillator. Not only that, but it looks very, very close to a parabola. In fact, almost all, even past halfway up, it basically looks like a parabola. It's only once you get past the halfway up point that you really start to sense and see that it's something else. So in fact, the parabola is a very good approximation, which is why we tend to use it for much of life. Not all life, but much. You asked me also about when do these fluctuations matter. You can see how now the particle has very low energy, but is confined here. It has some fluctuations. Those fluctuations might have a chance to take it over to the other well, and you might even measure it in the other well and then project it there. So this is where quantum mechanics starts to really play more and more of a role, because it's a nonlinear system rather than just a linear system. I can define an inductance as EJ, because then you end up with phi squared over 2LJ, where LJ is just related to EJ in this way. And that looks like the inductor part of the transmon. Good. Any questions?
So is this cosine thing like useful, or is it just like the only thing we know how to do? Like, would you rather it not have any more well?
Yeah, thank you, Robbie. It's good to see you. It is both, I think, a rich blessing and a terrible curse, depending on how you looked at it. For the transmon, it's a little bit of a curse because it leads to something called charge dispersion or phase slips sometimes, but you can also use it to create much more elaborate potentials. So there are other qubits like the plutonium where you try to create a more protected state by putting it in two of these wells, making the other wells less accessible. And, depending on the problem, as most things, it can either be your blessing or your curse.
Okay, but just to sort of like zoom out a little bit, like if you could build the ideal oscillator, you would do that.
If we could build an ideal nonlinear oscillator with just the Hamiltonian terms that we want and not all these extra Taylor terms.
Why do you want nonlinear? What's wrong with just building the?
Yes, because I don't know if you were here in the first part of the lecture. Okay, we went over how if you have equally spaced energy levels, and you shine light at them, the laser, then the atom will go from 0 to 1. But once it's in 1, it will go to 2. So you have no selectivity. You can't make a qubit out of a linear system.
Yeah, I have a question. So for the Taylor series, I mean, your flux has to be extremely small since phi naught is so small, right? So does that cause issues?
So if you remember the picture of the dilution bridge we saw at the chandelier, the golden chandelier, there was a metal can which tries to shield the magnetic external flux. I see Michelle.
I don't think we have problems with the
and smaller, actually, it's essentially the result of the magnetic field in the loop, which is just the diameter of the hair. So, I speak in microelectronics. So I would say that the first one is not particularly small.
So then how do you keep a pretty good approximation? Because you're taking a Taylor series, right? It's like the flux over phi naught. Phi naught is really small. So then you just get a lot of it.
Phi naught is not small. So phi naught equals 1. Perfectly reachable.
Yeah. But then you get a bunch of information.
Well,
from this parabola picture.
The cosine is a very converging function.
Yes.
I
I think we're about to do this exactly. It's an excellent question. I think just for everybody, in case you didn't hear what Michelle said, Michelle pointed out this 10 to the minus 16 may look small, but if you actually put a loop the size of a human hair, and you put it in Earth's magnetic field, it will give you this amount of flux roughly. So in fact, it's not that small, especially if your structures are nanoscopic. And so you'll see that in what I will cover, the flux excursions will only be down here in this region. They will never be very, very large. But let's get to it in this next slide. So following the logic exactly the same as we did for the classical oscillator, I'm now just going to do the exact same steps. I can write down, first of all, the classical Hamiltonian. I won't do all the steps for you, but basically there's no surprise. Q squared over 2c minus the energy, right? It's the energy of the capacitor minus the energy of the inductor, no surprise. You can also write down the classical potential picture with the semi-classical picture with, omega naught equal to 1 over LC. And you'll see that now if the particle in the semi-classical sense no longer lives on these nice circles, but kind of has these ellipses, and eventually it goes into some kind of open trajectory. So clearly this is very different when we begin to evolve and rotate. But let's actually work out in the next 10 minutes at a high level what this will look like. So let's take down just the quadratic part in our Taylor series and the leading order nonlinear piece, which is this phi to the 4th. Everybody okay? This looks good? Okay. And in fact, I'll do a change of variables. We spent a lot of time looking at how to write phi and q in terms of A and A dagger. And if you take the equations that we had on the previous slides, there's no other magic. I just did a substitution of variables. And you rewrite everything here in terms of A raising and lowering operators, you get h bar omega naught, A dagger A. So this is the classical harmonic oscillator. I dropped the 1/2 constant factor. And you can now rewrite the 4th order nonlinear piece. And what you get out is this small phi ZPF. It's the reduced magnetic flux fluctuations of the junction times EJ divided by 24 times A plus A dagger to the 4th power. So you'll see in a second why we did this transformation from phi's and q's to A and A daggers, because they're going to allow us to see very cleanly what happens with this nonlinear piece. Let's go ahead and expand the term. So you can write out that phi to the 4th term, or A plus A dagger to the 4th. And you notice that first you get all the terms you expect, like A to the 4th, A dagger, A cubed, and so on. And however, you also notice that A and A dagger do not commute. They have a commutator which equals 1. So if you want, you can use that commutator relationship to put all the A daggers on the left, which is called normal ordering, which then causes you to get some extra terms that do not exist classically, right? These terms are generated from the commutator. So in fact, these extra renormalizations do not exist in a classical harmonic nonlinear oscillator. Okay, thank you, Eli. We now go back to our picture. This is why I was insisting on sometimes you want to think of the A operator as a rotating operator in the Heisenberg picture. You see where you have some natural frequency of oscillation, e to the minus I omega naught t. So if you go into this rotating frame, which will feel natural because remember, it's just that red dot and oscillating around. And you look at all the terms that do not oscillate at zero frequency, but oscillate at high frequency, and throw those terms away, because you can say, well, they're going to oscillate at 5 gigahertz. That's very, very fast. They're going to average out to more or less zero, at least to a leading order. We do this all the time. The only terms that survive are the ones that have an equal number of A daggers and A's together, right? And this is called first order rotating wave approximation. It's exactly equivalent to first order perturbation theory in this case. Good. So the reason I'm going to drop this A squared and A dagger squared is because I'm making an approximation that to leading order, these terms rotate very fast. And so more or less they'll average out. I haven't actually proven it to you, but you see that it does work. Any questions? Good. So then we drop those terms. And so what we're left behind with are two terms from the nonlinearity. One which looks exactly like the linear energy, and one which has this A dagger square, A squared term. And so in fact, the Hamiltonian of the transmon qubit to fourth order in the Taylor expansion within the rotating wave approximation, this is the standard thing we tend to use, by the way, don't oftentimes need to go further, is the harmonic oscillator renormalized by some quantity, I'll call it delta Q here, due to the nonlinearity and the commutator. So this is really a quantum shift, it's called the lamp shift. And you also have a nonlinear piece, which is due to the nonlinearity, which you can express or write down as related to, again, phi ZPF. So when I said that the zero-point quantum fluctuations are going to dictate almost all the physics of the transmon, this is the first evidence. You see the nonlinear term, the nonlinearity depends directly on phi ZPF, and the renormalization of the linear frequency due to the quantumness of the oscillator and its nonlinearity also depends on phi ZPF. So in fact, what we do is we engineer phi ZPF and omega naught. That's circuit quantum electrodynamics engineering in a reduced nutshell. Any questions? So we call this the lamp shift, and we call alpha, this expression, this prefactor here, the anchromonicity. Why do we call it the anchromonicity? Well, because you can take this is the same expression on the earlier slide, simply rewritten in terms of that term n, which is the number of photons and the number of quanta of energy, if you want, in the oscillator, which I had mistakenly written down as a diagonal matrix with 1, 2, 3. It should have been 0, 1, 2, 3. That same operator. Now you will remember it forever. And you can write down the second term as n squared minus n. And you notice this term only acts if n is greater than 1. See, if n is 0, this is 0. If n is 1, this is 0. So it only acts for higher energy levels. That's nonlinearity. That's anchromonicity. Right? So this is the linear Hamiltonian and the nonlinear Hamiltonian. We know everything about the linear piece. We just spent an hour and a half on the harmonic oscillator. Everything new only comes from this nonlinearity. But in fact, this nonlinearity is, you see, and it's in the same basis. It's diagonal. You see, it's another n operator. So to first order, it won't even change the. So if you do perturbation theory to first order, you will only change the energies here, or you will only change the energies in this point. You get. So what does the energy look like? So now if you put in a quantum eigenstate of the harmonic oscillator called n, let's say 0 quanta or 1 quanta or 2, the energy of that under our effective Hamiltonian is simply the energy of the harmonic oscillator driven down by or renormalized a little bit by the anchromonicity that only acts if n is significantly greater than 1.
Just, there was a question to show the previous slide.
Okay, the question is show the previous slide.
Yeah.
Okay. Good. I hope that answers the question. Good. Yes, I see Michelle. Yes, please. Yes, so for big N, I mean the operators. So big N hat is the operator, and then little n here is the eigenvalue number, the eigenvalue. Is that okay? Okay. Good.
Question.
Yes.
So why does the energy for n equals 0 is 0? Is that because of the shift?
Why is the energy?
In the last expression, if we substitute n equals 0,
I'm sorry. Where?
H4 RWA.
Yeah.
No, the next expression.
This expression.
Yeah. So for n equals 0, we get an eigenvalue of 0.
Yes. Because yes, good question. So energy is not an absolute. So I have subtracted off, or you can. The only thing that's measurable are the energy differences typically. And so I've subtracted off the absolute 1/2 h bar omega naught. So technically, if you want, there would be a constant term here, but I'm only interested right now in the energy differences, so I just subtracted it to make this cleaner. If you want, what happened is that in the previous slide over here, there should be a plus 1/2 h bar omega naught over 2. Plus h bar omega naught over 2 times the identity operator. But I've taken that off, or if you want, I've moved into a gauge or a frame where that term is gone.
It's just the global phase, right?
It amounts on, yeah, for a single system, it amounts to global phase on the wave function. Good. I see we're running a little short on time here. So maybe to put some experimental parameters and connect to the earlier slides where we saw example devices from people. Typical, what you might ask, what are the typical values that are used in the community? And they're usually very, very close, especially for a trans-1 qubit to these. These are ones that I used to, I used in my PhD thesis in Michelle's lab, actually. So it was 14 nanohenries for the inductor, 65 femtofarads for the capacitor. You might ask, why is that? Well, that's because if you now write them in terms of energies, you see that the Josephson energy is 12 gigahertz. It's much bigger than the charge energy of 0.3 gigahertz. And so if I plot the wave functions of just the harmonic oscillator in here, they're pretty well localized, right? You have to think of these as the spring and mass system. The mass is heavy enough to where the particle is pretty well localized at the bottom. So I think this is exactly the wave functions for the harmonic oscillator for these experimental parameters to scale, I believe, if I plotted it right. You see that in the vacuum state, the excursions are quite small, right? You're really exploring a very, very parabolic part of the cosine potential. And then the one state looks also like its excursions are quite close to the parabola. The two state will explore a little further, so it will be more sensitive to the parabola opening up in the cosine, but just by a tiny bit. Of course, as you get to energy levels that are like this fourth energy level, which is quite high here, it will, or I've just shifted it up, but you have to think of the probability across this variable. It will become more and more sensitive to the fact that the cosine potential is opening up and it does not look like a parabola. And that is why you see this shift, because you're sensing the fact that you're in a cosine more and more rather than in a quadratic potential. And so for this qubit, the frequency was 5 gigahertz, the anchromonicity was 300 megahertz. And its effective impedance here was a large number of ohms, 450 ohms. Good. Yes, you might ask, how much does 0-point fluctuations happen for both the charge and flux? Well, you see that in terms of electrons, what this says is that across that Josephson tunnel junction, the 0-point fluctuations are about a single Cooper pair or 2 electron charges. we're really thinking of vacuum fluctuations on the order of single electrons. That's the amount of net charge that's oscillating. And for the flux, it's about half a flux quantum. So really quite close to fundamental units. Okay, good. So that is, in the interest of time, that is the end of the story for the transmon qubit as far as we will get to today. So let me just take any final questions on that. Yeah, one quick question.
Can we engineer this EJ to just accommodate only 2 levels?
Great question. So in different types of qubits, you play with EJ and EC, and you can make only 2 levels in the wells. You can make 50 levels in the wells, and then you have to think of the trade-offs of, the system becomes more linear, right? If you have very many levels in here, it looks like a harmonic oscillator. If you make 2 levels in here, what happens is that the higher level can easily tunnel to the neighboring well, and then you have to be careful about that, for instance. And it's very nonlinear. So, Eli?
Just a question from online, which I think is a nice follow-on to this. What is our target impedance?
What is our target impedance? So it is a bit of a gauge, as I mentioned. It depends where you look at the system from. You notice that in this example, it was about 450 ohms. So I think that's higher than free space impedance. You typically want to set this ratio so that you have a heavy enough particle for the transmon qubit, because you see all these parameters are linked. Really what you care about is the frequency of the qubit and the anchromonicity. Because if the anchromonicity is the energy level difference between 0, 1 and 1, 2 is if that anchromonicity is very small, you cannot do a fast pulse or a high pulse, because your pulses are all frequency. If your pulse is very fast, it has a very big frequency component. And that means that you will be able to not just drive 0 to 1, you'll be able to drive 1 to 2. So your pulses need to be frequency selective and be able to only go from 0 to 1 and not 1 to 2. And so that means your pulses need to be much narrower than 300 megahertz, typically. Of course, you can play fancy tricks with pulse shaping, but that's the basic idea. I know that we are very much at the end of time. So let me just give you in 3-minute overview of where you can dive deeper on these things and what will be covered later in the workshops. And we'll just end there. First, if you want to go deeper on the transmon qubit, here we could just scratch the surface. You'll hear all the rest of the talks, and I hope this is giving you the foundation to go through it. I posted a slide with kind of a continuation of these lectures at this QR code. And then what a lot of the rest of the workshop will be, and really what the advanced track is covering, is now how do you begin to automate all of this in actual software? And how do you begin to treat these systems in the design space, especially when they're distributed? And we begin to use different simulators, which effectively do all of the classical Lagrangian and Hamiltonian for us. And we then can either look at the eigenmodes of the classical system, purely the linear system. Usually we just look at with the linear system. You can look at different models where you can extract capacitances or inductances of these distributed systems. So really the advanced version of this is to do everything we did with software with more precision on the distributed structure. If you have wire bonds and bump bonds and so on. You can look at impedance analysis too. But it's all the ingredients that we've already looked at that get you to a total system Hamiltonian. And fundamentally, there are only 2 ways to do this that I know of. You either break up your system as we did into a linear and nonlinear piece. You solve the linear piece and then you add the nonlinear, or you try to do it in terms of a system, kind of like we did the harmonic oscillator and some interaction between the systems. There are many different techniques. There's a whole landscape. There's not a single king to rule them all, or queen if you want. There are all kinds of different techniques that come with more information and accuracy or more speed. So typically we use a lot of them at different stages of the design. Most of these are automated, which is really nice. So you don't have to actually write these. You just have to know what they're doing which is what we're doing the foundation of today, there are many, many tutorials online. This is just a small subset of the ones we find. And you can do analysis with impedances, as we touched on very briefly, or eigenmodes. You know, we looked at the harmonic oscillator eigenmode, that's what we did. Or you can look at capacitance, inductance, and structures. And you can essentially repeat the steps we did, but with usually distributed structures where somebody else has worked out a big part of that workflow for you. So we don't have time to get through all of it. I'll just highlight again that I hope you will in the future begin to contribute to the open source space of quantum device design, and send me designs that you make with some of these tools. I love to showcase them and show people and power the community. I believe we're going to have a lunch discussion also about the future of open source software beginning today, if you like.
Yeah, I'll put an announcement out, but anyone who is interested in these maintainers groups, we are going to have a breakout session tomorrow, but we'll also just start chatting during lunch. So if you're interested, find me, find Zlatko.
That's right. And so with that, I will leave you with this quote, and I hope that you learned at least one thing. And my message to you is stay curious, keep learning. Thank you very much.